we're going to learn how to find the length of the graph of a polar function, or in other words, the length of a polar curve. If we start with a polar curve described by r equals f of theta, where theta is between alpha and beta, the first thing we want to do in order to understand this length is write it in standard polar form, using theta as our parameter. How do we do that? Well, let's see. We start by writing the standard transformation equations. X equals r cosine theta and y equals r sine theta. Of course, when r is f of theta, that just means x is f of theta cosine theta and y is f of theta sine theta. And just as we had before, theta here runs from A to B. This is a standard parametric representation using theta as a parameter. Now, how do we find the length of a curve when we have a parametric representation? Well, the length is just the integral from A to B of the square root of dx d theta squared plus dy d theta squared with respect to theta. We can just use the formulas we had before and plug them in here, but it'll be much easier if we first simplify this formula that's under the square root sign. So how do we simplify that? Well, remember, I'll rewrite it here, x was f of theta cosine theta, y was f of theta sine theta, and because of that we can compute using the product rule. Dx d theta is just f prime of theta cosine theta plus f of theta times minus sine theta. So instead of the plus, we'll turn that into a minus. And similarly, we can write dy d theta is f prime of theta sine theta plus f of theta times the derivative of sine theta, which is cosine theta. Now, what we really want is dx d theta squared plus dy d theta squared. So I'll put those over here. What is dx d theta squared? Well, it's the square of this formula. So we get the square of the first term, f prime of theta squared cosine squared theta, plus the square of the second term, which is f of theta squared sine squared theta, plus the cross term, which in this case is minus 2 f prime of theta f of theta cosine theta sine theta. Similarly, we can write dy d theta squared as the square of the first term here, which is f prime of theta squared sine squared theta plus f of theta squared times cosine squared theta. And then we add the cross term, which is twice f prime of theta f of theta, and we'll have a cosine theta times the sine theta. When we add these two together, we get the formula that dx d theta squared plus dy d theta squared is all of this plus all of this. Notice that these cross terms cancel, and we just get this term plus this term, which I will write the first term from each part, gives us f prime of theta squared times, here we have a cosine squared theta, and here we have a sine squared theta, plus using the second term from each, we get f of theta squared times sine squared theta plus cosine squared theta. And again, this cross term cancels. And of course, you remember cosine squared theta plus sine squared theta is 1. So you end up with nothing but f prime of theta squared plus f of theta squared, which we can write in this other form. F of theta was just r, remember. So this is r squared plus f prime of theta squared, which is dr d theta squared. That tells us now that we can find the length of the polar curve just by integrating from a to b this quantity, square root of dx d theta squared plus dy d theta squared d theta, and we just solve for that formula under the square root. That's the same as the integral from a to b of r squared plus dr d theta squared with respect to theta. Let's look at one quick example of this. Let's look at the graph of the polar function r equals cosine theta, where theta goes from 0 to pi. Now I put the picture of the curve here, and it's pretty clear it looks like a circle. And I think this is one you've seen before in an earlier video lecture. But let me remind you here, when theta is 0, we have r equals 1. So we're going to start here when theta equals 0. When theta gets all the way to pi over 2, we're down here at the origin. When theta equals pi over 4, we're actually way over here at the point whose polar coordinates are pi over 4 and 1 over root 2, which is cosine pi over 4. Those are the polar coordinates of that point. So we're moving along the circle, starting at this point on the right, going to the left at theta equals pi over 2, when theta equals 3 pi over 4. Let's see. We're down here, and then when theta equals when theta equals pi, we're back at the point we started with. So as theta runs from 0 to pi, we go around this circle exactly once. How do we find the length of this curve? Well, the length is just given by an integral, in this case from 0 to pi, of the square root of r squared plus dr d theta squared d theta, which is the integral from 0 to pi of the square root of r squared, which is cosine squared theta, plus dr d theta. Dr d theta is minus sine theta, and we have to square it. D theta. And it's pretty clear that under the square root sign, we have cosine squared theta plus sine squared theta, which is exactly 1. So the whole integrand is 1. And we have the integral from 0 to pi of 1 d theta, which is clearly pi. Is that going to be the right answer? The answer is yes. This is a circle of radius 1/2. So the circumference, which is the length of the curve in this case, is 2 pi times 1/2, which is exactly pi.